I'm Rob Lyndon. I became interested in deep learning, which is a kind of a blanket term for a range of machine learning technologies, including deep belief. I became interested in that through my work in the London F# user group. So for that reason, Vulpes, my open source project that I'm going to tell you about today, is written in F#. That's probably a little bit too honest for the audience, right? So I wrote it in F# because I'm part of the user group. Okay, well, rewind that. Just pretend I never said that. If you did ask me why did you write it in F#, I'd give you a more convincing answer, a better sales pitch, which is, there's several reasons. One, the main one, which is a deal breaker, to be honest, is there are libraries that let you do the work on the GPU. Now, if you're doing machine learning, you have to work on the GPU. Forget trying to do it on the CPU. This is massive matrix multiplications. You're going to need the speed the GPU gives you. Now, one of the issues with the GPU is, of course, that it's a bit of a can of worms. GPU programming, for anyone who's done it, how many people have cut their teeth on GPU programming? So about a third of people. Anyone who has knows that it can be a bit of a can of worms. I have damaged my laptop so badly that I've had to fiddle around in the BIOS trying to get it working again, having done GPU work. So given that that's such a can of worms, it gives me a lot of security and comfort to be working with a very strongly typed static language like F#. This is a good thing. F# is, I mean, it's not extreme static typing like Haskell, but it's much more towards the static typing end of the spectrum than most functional languages. But it's got composability in, which, as we'll see later, is a very good thing. Now, I'm not saying here that I'm angling for contributions to the project, but you know, if you ever feel like wandering over to my GitHub and asking me out for a coffee over there and seeing how it goes, then come over. I'll give you the address at the end of the talk. It's open source, and if you want to do some cool, if you want to do some machine learning in a cool language like F#, then this is a good place to start, especially if you're a good front-end developer or you've got any experience at all in Web Sharper. Web Sharper is a set of tools for writing fully fledged front-to-back web apps in F#. So on the front end, it translates it down to HTML and JavaScript. Right, let's try. So let's take a quick look at, going to give a quick potted history of deep learning and start at the end. So where are we now with deep learning? It's nice to, if you haven't done this already, just go and have a look at the images search in Baidu. What you can do is you can take photos from your camera, you can upload them to the Baidu search engine, the Chinese Google, and it will tell you what it thinks your image is. You know, this is quite powerful, and that's an example of a deep learning technology that's up there in the wild right now. For Vulpes, I've gone back in the level of sophistication. I really work on MNIST, which is the hello world of machine learning examples. MNIST is it's a database of handwritten digits. There's a training set of 60,000 handwritten digits from a statistical sample that was carefully randomized. And the test set is 10,000 images written by different people. And the idea is you run it on the training set, you identify these handwritten images with the numbers they're supposed to be representing, and you train your neural net on the training set, and you see how well it performs on the actual test set. And as you can see, some of these numbers are written by a handful of volunteers. This 9, ask me any time, I would have told you that's an 8. So it's actually quite surprising that the good machine learning algorithms now outperform humans on the MNIST data set. And actually the level of success now in good systems is down to about 1%. And really I think when you're comparing a success rate of 0.8% to 1.1%, I think that's really noise. I think you're basically by then assessing the quality of the experiment rather than the quality of your network. So networks today, they've moved beyond MNIST. They really test themselves on things like ImageNet, which is a database of 15 million labeled images taken from all over the net. And that's what the cutting edge tools are really working on. However, MNIST is still, it's still useful. Still useful if you're, like I was in F#, writing a neural net from scratch, and you want to work out how it's doing. I think I'm down to about 4% errors or something at the moment. And it's also useful for if you want to just see how a neural net works, how the edge detection features work at the lower levels. Then MNIST is a very useful way of just showing how this feature recognition, feature detection actually works. So it has its uses. It's worth saying that the deep belief net algorithm is not, of course, confined to image recognition. At its core, it's generic enough to handle pretty much any set of inputs. So one thing I've done in Vulpes, which is a difference between now and when I gave this talk back in April, is I've added a concrete layer of indirection, so that the layer that knows this is looking at the MNIST data set or vision recognition is actually quite small. So the core of the system works on inputs, outputs, and signals, and calls them inputs, outputs, and signals. So if you want to if you want to say, right, well, I'm going to start looking at TIMIT, the speech recognition data set, or I'm going to look at a whole different classification problem, like here's someone's medical records, are they a risk for breast cancer or not? The same algorithm can still work for those kinds of examples. So potted history of neural nets. I mean, I say 1960s here. Actually, Frank Rosenblatt came up with the perceptron. I think there was a paper in 1957 was his first introduction to the world of artificial intelligence and machine learning. It caused, at the time, a lot of excitement, which later on turned out to be ill-founded because the problem was more complicated than they imagined. But the idea is, if you've got an input vector, just a piece of data, x1 up to xn, you multiply that by a set of weights, take a dot product. The j subscripts here that denotes a place in your, denotes an iteration step. So your first guess is w1 naught, w2 naught. Take a dot product, feed that through an activation function. If you exceed the threshold, then you get a 1, you get a firing. If it doesn't exceed the threshold, you get a 0. So that gives you a kind of two-stage classification problem. And the perceptron, what it will do is, if that's a training set on your left, you know whether or not you expect the neuron to fire. And if it does fire when it's not supposed to, or if it doesn't fire when it is supposed to, you can update the weights accordingly with that. And that is the core of your algorithm. Now, that converges as long as your test set is linearly separable, or your training set is linearly separable. And so for 2 dimensions, that means there's a line that separates the 2 sets. Higher dimensions, it means there's a hyperplane that separates the 2 sets. And in fact, in higher dimensions, that's not quite as restrictive as it is in the single dimension. But there's a huge class of problems for which the perceptron just can't converge, and one of which is the XOR problem. And that's really one of the reasons why, after the initial euphoria and the predictions of robots making cups of tea for you in the morning, the excitement died away, and the whole field kind of atrophied for a little bit. Fast forward then to the 1980s, and along came a paper, again, Jeff Hinton's name always comes up with this, who worked on the backpropagation algorithm. And this is a form of layered learning. Now, this is, the idea here is you start with your set of, your input signal, if that's that could be an image that's your input signal. And from that, instead of trying to go straight for the final answer, you take more than one vector of weights. You take a set of vectors of weights and use that to generate some hidden units, like an impression of the first input layer that you started with. And then you can use those hidden units, that impression of your first layer. You can use another set of weights to get an impression of that layer, and so on and so forth, until you arrive at your final impression. And again, if this is a training set, you can take the difference between the target that you're expecting and the actual value at the end of the chain, and use the chain rule to go back down and get weight updates all the way back up the chain. Now, turns out that actually the problem of linear separability doesn't happen in this. This gets around it. And in fact, Rosenblatt knew that that was the case all the way back in the 60s, but there's been controversy over whether he did know that or not. It's worth just taking a little while to say this is a stronger model, but also just kind of think about, well, what's a kind of biological interpretation of this model? And I guess, you know, if you imagine that you're waking up in a dark room, you're not really perceiving where you are. You're in somewhere new. The first thing you're going to start noticing is lines and curves, and that's basically your first level of hidden units. That's the first initial impression you get. Then, once you've taken stock of all of those, then you start moving up the chain a little bit, and you go from lines and curves into shapes, triangles, rectangles, color regions. And then from then, those shapes, you can start going further up the chain and picking out individual features. And so those triangles and circles and rectangles and ovals might suddenly start looking like eyes or noses. Go one level up from that, you kind of aggregate those into a face. And then one level up from that, you recognize the face. Okay, that's my wife, that's my cat, that's that guy on the telly. And that final level of recognition is your kind of top layer. There is a school of thought that says you can see what happens with the lower layers if you take acid, which I'm not suggesting that anyone does, but the school of thought says that what you're doing when you take acid is you're actually scrambling the kind of the V1 and V2 layers of your visual cortex. Again, I don't recommend it. Now, let's step back from this a bit. I mean, this, okay, who's been to talks on machine learning and who's seen this picture? I mean, this might as well be a logo for machine learning. It's very, very familiar. I mean, remember, I started this project in my bedroom, so I want to give you a feel for actually how I interpret this model. So I want to dive a little bit deeper into the backpropagation algorithm before we move on to belief nets. Problem with the backpropagation algorithm can be slow. You've got to drive up your matrix all the way through the layers to the top. Then once you've got your deltas, once you've got your error signals, you've got to drive it all the way back through the layers. That can be slow. You can end up in very bad local optima. You can basically, yes, you'll get convergence, but you can end up converging to garbage. Possible problem. Anyway, let's have a quick look at how we generate hidden units in practice. Go back to this idea of the MNIST database. Now, the MNIST data set, it's basically some 28 by 28 images. So you've got 784D vectors, effectively, and the values are in the closed interval 0 to 1. And that's your input signals. And basically, Vulpes works on input signals that are vectors with values in 0 to 1. So as long as you can take initial signals and convert it in that way to a vector like that, then you can run a backpropagation algorithm and a deep belief net. So the hidden units are built up like this. So I'm thinking of the hidden units as binary variables. Binary variables, they're either 0 or 1, and the probability that the neuron is going to fire, that the hidden unit is going to be activated, is given by the sum of the weighted sum of the input layer plus a bias, and then you run that through an activation function, which generally speaking looks like this. It's monotonic increasing, it's bounded above by 1, it's bounded below by 0, and as long as you have a function that satisfies those criteria, that's a decent activation function. Again, when I first looked at this, I was sort of confused by bias. You know, what does bias mean? And it took a little while to click. The clue is in the word, right? So if you're biased about something, just in the everyday sense of the word, that generally means you've made up your mind before you've even heard what the issue is. So if you imagine that bias is a really huge number, if it's a million, billion, trillion, then whatever the input is from these VIs, the bias is going to overwhelm those signals, and that neuron's going to switch on whatever happens. And similarly, if it's minus a million, billion, trillion, then you've got a negative bias, and that neuron's never going to fire. You're not going to see what's in front of your face. But you know, just for the sake of mathematical elegance, we can actually incorporate that bias into the weights matrix by pretending that we've got a V0, which is 1, always 1, and then we can just tack the biases onto the left-hand side of our matrix and add a new column. The biases become weights, and mathematically things start to look very elegant. Here I've got kind of a weird hybrid between maths notation and functional programming notation. So we take our visible unit vector, we prepend a value of 1 on it for a bias, and then we apply the activation function to the dot product of the weight and that prepended vector. So there you go. That's the feed-forward stage of our backpropagation algorithm. That's how it actually works, and that's how it's implemented in Vulpes. I wanted to go into that level of detail because I couldn't find anyone actually explaining that to that level on the web. And I'm not very bright, so it took me a while to work it out for myself. Okay, so that was the 1980s breakthrough. Moving forward to 2006. 2006 is the date that everyone talks about in machine learning, because that's when belief nets came around, invented by this chap, Jeff Hinton, not to be confused with his doppelganger. I apologize now. I actually stole this joke from one of the engineers at Baidu. And I have to be honest, I got the impression from this guy that Jeff Hinton is basically the rock star of the Baidu engineering community. I think if he showed up, they would mob him. Now, his contribution, I mean, maybe it was his grad student, I don't know. But his contribution to the field was changing the question a little bit. He said, well, what configuration of hidden units, if we've got a set of visible units, rather than thinking about moving up the chain from hidden units, from visible to hidden units, he said, well, if we've got an input vector, what's a set of hidden units that gives us the clearest picture of this set of visible units that we've got in front of us? And that's a subtle shift of emphasis. So we're not trying to get the right answer anymore. We're not trying to say, this is a dog, recognize it as a dog. We're just going to say, right, okay, take an impression of this image that I've given you, this input, and get the impression that really captures the most information that we can get from that initial image. And then choose your weights with that goal in mind, rather than an attempt to try and put a label on something before we really know what it looks like or feels like. And the real breakthrough came in the fact that rather than having to travel all the way up through a network, you can do this kind of layered learning a single layer at a time. So you can kind of work on reducing the dimensionality at the lower level. This is typical set of parameters that you have. Once the job is done at any one level, then you take the weights that come out of that you've corrected for each level. You can use those weights to feed the input through to the next layer, and then you can treat the next layer in exactly the same way. This is called greedy layer-wise learning. And as you can see, each successive iteration, because we're dealing with lower dimensions, is quicker than the previous layer. So that's unsupervised learning, that's pre-training. And you know, it kind of makes sense, again, tying it back to psychology. You know, we learn what a dog is long before we actually learn that it's called a dog. So this is this pre-training step is really quite a useful idea. And what you can do is you can run this simulation. You can get an initial set of weights, then you feed back into your backpropagation algorithm. The backpropagation algorithm is still the workhorse of the machine learning community. And that is the supervised learning stage. So a typical deep learning would use a deep belief net to do the pre-training. And then once it's got a decent set of weights, then it can put those weights that it's learned into fine-tuning, into supervised learning, and then it can start learning proper labels for all of these things that it's learned to recognize. And that avoids the problem of those bad local optima. So the restricted Boltzmann machine is the kind of magic ingredient of the deep belief net. And a restricted Boltzmann machine, it needs two features that really let it work its magic. And those two features are that the hidden units have got to be independent of each other, and that for your sigmoid function you have to have a very special activation called a logistic sigmoid. It's a very common function in all areas of statistics. And as long as you have those two conditions met, your restricted Boltzmann machine, your single layer, can work a really nice piece of magic. And this is what the magic is, right? So like we said, we've already seen what the formula looks like for going forward up the tree. We've got a weights matrix. The probability that the hidden units are going to fire given a set of visible units is determined by that weights matrix. But here's the really cool thing about restricted Boltzmann machines. It works the other way. So given a set of hidden units, that same weights matrix that you've used to generate the hidden units from the visible units can be used to generate the visible units back from the hidden units. You can go up and then back down the network with the same weights matrix. You've got, as I say, you've got biases there. That's fine. You can incorporate the biases. The B's can become the left-hand column of your big weights matrix. The A's then become the top row. And then once you've got that, you've got a single set of weights taking you forwards and backwards through the machine. And there's a couple of lovely kind of elegant, beautiful closed-form formulas that let you start traveling through your net. So, what do our updates look like? We're nearly there. So how do you get your weight updates? Well, what you can do is you can travel forwards and backwards through your machine until you get convergence or until the end of time, whichever comes first. And then given that, you can take an outer product of the visible and hidden units, 1 and then at infinity, subtract the 2, and then you've got your weight updates. Waiting till the end of time, I mean, it's fine if you're Doctor Who. Slight problem if you're the rest of us. Now, what you can do is you can do this. It just turns out that actually up, down, up is enough. And I feel guilty about being so glib about that because it took Jeff Hinton a long time to realize that was the case. And it took him even longer to mathematically prove that that worked. But for us, we don't care. Right? It's just enough for us that it does work and that you don't have to worry about V infinity, H infinity. These are the updates that we're interested in. This is our gradient function, the 1 minus 2. We have it. Well, not quite. There's one little point. You don't want to end up overfitting your data. You don't want to end up with a set of weights that fits your training set perfectly, and then as soon as you have a tiny deviation from your training set, it gives you garbage again. So you have a momentum term that helps you to overcome any of these problems with overfitting. The momentum term basically remembers what the last update was and gives you a small contribution in that direction to your next update. So that's what it looks like. This is what the formula looks like. It's really quite nice and simple. This log derivative is the weight update from the outer product, and the alpha times delta Wn is your a weighted sum of your previous work. Now I've seen a MATLAB implementation of a deep belief net that had etas and alphas actually written in the code. To which I say, well, look, we're not mathematicians, we're software developers, right? I've got a better name. If you're going to have a learning rate which is eta and a momentum which is alpha, how about a better name for that, which is learning rate and momentum? So those are the things that you're going to find in the Vulpes code. There's no etas and no alphas, no Greek letters at all. Yay. Right. So this goes even further, and this is now kind of wandering into what Vulpes does. I use discriminated unions. And that means that I have a set of parameters that I express as types, and then when I have a function that takes any of these parameters, they're not expressed as primitive obsessed ints. They're actual parameters that feed into my machines. So this is where the functional elegance of F# helps you write very robust code. Remember I was saying earlier about having a statically typed language that really helps with machine learning. So that's what this looks like. To do matrix multiplication, we've got to use GPU. Best analogy I've found for learning GPU is think about a plumber. And the reason it's a good analogy is because when a plumber's in your kitchen, they can get tools out of their bag. That's an analogy for memory in the most local cache. But they might have to go out to their van to get a tool. He might have to go back to his workshop, drive all the way back. He might have to order parts from suppliers. And there's analogies between those processes and going back to different levels of your cache, different levels of memory on the CPU. The GPU has a different approach. That means you invite thousands of little plumbers into your kitchen, and they all are equipped because you equip them all with the small amount each one needs. Now in CUDA C, a kernel would look like this. The little plumbers would be, that's obscured here. There's a CUDA C has a _ global that tells you you're in a kernel, and that means you're running off device memory. So the pointers up there, I don't know if you can see that, but there's pointers in the signature of the kernel that are on the GPU threads, and you activate that from the CPU using CUDA malloc and CUDA memcopy. Now notice that this is one of the issues with CUDA C that I don't like. On the one hand, we've got pointers to device memory. On the one hand, we've got pointers to host memory, but the compiler can't tell the difference between the two. And that can be a source of very strange bugs and problems. So I use, so this is two levels of reality here. There's host and device, big plumber, little plumber. Now in F#, you've got more sophistication. I work with something called Alea Cubase. That's the URL, that's the web URL, QuantAlea.org. And you write kernels slightly differently in Alea Cubase. You use them using code quotations, which are basically expressions. They've got all the metadata, and you can create a code quotation at runtime. So the output of this function, binary operation kernel, is actually a CUDA kernel that you can fire up with your own launch logic. So in this case, as I say, before when I was in CUDA C land, you had to write a specific kernel to add two vectors together, right? That's the adding two vectors is the hello world of the GPU programming set of problems. So here I've got my binary operation kernel. I can actually feed in an expression into that function, and then at runtime it's going to create a kernel for me out of that expression. So that's an advantage over the C language CUDA specification. Another example is that you've got strongly typed pointers. There is no way in CUDA here that I can mess things up by passing in a pointer that doesn't point to an address on the GPU. So this is how you'd build. This is how you'd build one of these kernels at runtime. The let bang basically says that you're in a that's a syntactic sugar for a bind operation of a monad, and that leads you on to the next topic, which is saying, look, in Alea Cubase, we don't just have the host, the big plum, we don't just have the device. We've got a CUDA monad, which is like a marshalling layer between your big plum and your little plumbers. And that manages all of your launch logic and the mappings between your host memory and your device memory. And that's really, really handy for building my deep belief net with F# using Alea Cubase. So as I hinted at the beginning, here's where we get the composability of a functional language, and we can really turn it to our advantage, because the output of one kernel becomes the input of another. And that's great, because actually launch logic is cheap. What's expensive when you're doing CUDA programming is copying memory across from the host to the device and back. But if in your main loop, all you're doing is launching kernels and using the output of the previous step as the input of the current step, then you're in a really good shape. I think it takes about 70 microseconds to launch a kernel. So this is immediately a good thing. And let's look at a quick example of this. And this is the kind of thing that does happen in my code. If there's time at the end, I will show you some of the code base of the deep belief net that I'm working in. So if you imagine you want to add a vector and multiply the result by a scalar, this is the syntax you'd use in the CUDA monad. So you define the kernels. One of these is this binary operation kernel. And you have another scalar multiply kernel. The output of the monad is this function from x and y and a scale. And that function then, once you've built that function using the compiler, then you can use that function to do this operation. And it will do the operation. It will take the quantities x, y, and scale that are all defined on the CPU. It'll copy them over to the GPU for you. It'll do the calculation on the GPU. Then, using that gather function, it will give you the result back and translate it back onto the GPU. So this is how you would actually use the CUDA monad in Alea Cubase. It's extremely elegant. So I've got, in fact, that should be add vector and scalar multiply template. So that's the typo. Use add vector program is add vector and scalar multiply template. Load, compile that, and then when you call run, what you're doing is you're invoking this. I think this must be an old version of the slide that I've got, because I remember correcting this earlier. Never mind. There you've got your function that comes back. So all you need to do in real life is to call run on the add vector program or the add vector and multiply by scalar program, and then that does all the job for you and puts you in a good place. Gather and scatter, that's the way to copy memory between the host and the device. I'm going to say that, and of course you've got the worker.malloc, but worker.malloc internally will be calling the scatter function. Okay, so I think I'm going to try to just show you, I mean that's the toy example, but I would like to, if I can, show how this translates into code. Can you? However, I'm not sure that I can see my ID on the screen. Oh, there it is. Okay. Right. This is going to be interesting. Okay. That's fine. I'll locate the relevant piece of code, and then I'll put it on the screen. So if I go into CUDA templates,
if you want, you can duplicate the screen, and then we can see your Visual Studio. Like do Windows P and just duplicate the screen.
I'll tell you what. We're a little bit pushed for time, so I think I'm just going to do it the low-tech way. So running through this, seeing what the code actually looks like in practice. So this is the kernel. So the main loop, what happens is inside the main loop of the monad, you get to this loop that loops across the batches of inputs that you're looking at. And what you'll notice is all you have inside the main loop is launch logic, right? So you launch the forward iteration that takes you from your V1 to your H1. Then you go backwards to populate V2, forwards again, and again, look, it's launch, launch, launch. That's all it is. So we've got this composability going on very nicely here. Then you compute your C1 and your C2, your positive update and your negative update, add those two together, and then that gives you the weight updates. Then you move on to the next part. I do have a gather here, but that's just for reporting purposes. So every 100 iterations or so, you will gather the information, and then that tells you how you're doing in your simulation. So that is pretty much a potted example, demonstration of how I will work a deep belief net in my GPU. What I'm going to do now is give you my Twitter and the GitHub address. So if anyone wants to contribute or to have a look at the code base, then that's how you do so. If anyone's got any questions, fire them at me. Thank you guys very much for listening. Yeah.
I'm almost sorry to ask this, but does it work in mono?
Does Cubase work in mono? I think it does. Right? I can't stake my life on that, but the guys at Cubase are quite they're quite committed to making it work across as many platforms as possible. So I believe so, but do check the QuantAlea website to just make sure. So yeah, I think so is the answer to that question. Does Cubase work in mono? Anyone else? Yep.
So Vulpes is open source, but is the Cubase?
Question is, Vulpes is open source. Is Cubase? Answer, no. You can fire up a trial version of Cubase. And to be honest, the licensing isn't that expensive. I think I paid about £30 for a year or something like that. So I'm quite happy because I'm interested in this material to pay the guys. And to be honest, the help that they've given me in building Vulpes, it's worth a lot more than 30 quid. Put it that way. Cool. Yeah, a couple more. Go for it.
The operation graph that you're building to send to the GPU, like the thing that actually gets compiled in CUDA,
Yeah.
is that a value? Can you hold on to that, or is that just sort of implicit?
Is the thing that gets sent to CUDA. What gets sent to CUDA is a compiled function that you can then call.
Right.
And
like presumably, right? So you have your individual kernels and you're composing them together.
yeah,
That forms an operation graph.
yeah.
Is there a value that you can say this is my operation graph? For example, if you wanted to write like an optimizer that runs an operation graphs and transforms them into more efficient ones, like could you do that in a generic way, or would you have to like add some extra, abstraction for I'm going to put my operations in here?
I think, to be honest, you would have to do some extra work to do that.
Okay.
But again, that's a case where you get in touch with the Cubase guys, and they can tell you very quickly whether you can do something. Or sometimes they might decide it's worth doing a bit of extra work and helping you out with that. I mean, potentially they're going to have a look at providing an API to the NVIDIA's new QDNN, which is quite an exciting development. NVIDIA have basically announced a whole deep learning library that's going to be part of their interface. And as I say, it's very much in my interest to be able to access that from Cubase. Yeah.
Where are some good locations to get more papers on deep learning?
Go to Jeff. Loads of places, but the two best guys. Sorry, the question was, where's a good location to get papers and presentations for deep learning? The kind of superstar is Jeff Hinton. So if you go to Jeff Hinton's webpage, there's lots of resources there. His talks make sense when you've kind of dipped your toes into machine learning a bit more. If you're new to the field, I recommend talks by Andrew Nung, who's, I think, in the same department as Jeff Hinton, or has worked in the same department. His talks are still conceptually sophisticated, but I tend to find them more approachable than Hinton's work. Hinton's work does make sense, but I think it only starts to make more sense when you've got your bum wet in the code a bit more. Okay, and anyone else? Yeah.
Are you aware of anything comparable on the other platforms, specifically to Cubase?
No, I'm not. And nor a Cubase. I mean, I was talking to them in March, and I'm the only guy. Well, as of March, I mean, things may have changed, but as far as they knew, I'm the only guy who's doing any deep learning in their platform. Mind you, 6 months is a long time, so maybe that's changed. Okay. We're done? We're done. Thank you.